The program begins with a brief review of prerequisites. This program uses rectangular coordinates with a horizontal x-axis and a vertical y-axis to display graphs of polynomials. For example, on the graph of this polynomial, the vertical y-coordinate of each point is equal to the square of the horizontal x-coordinate. Here are more examples. Constant polynomials. Their graphs are horizontal straight lines. Linear polynomials, that is of degree 1, their graphs are also straight lines. The graphs of quadratic polynomials of degree 2 are called parabolas. Cubic polynomials of degree 3, these graphs are called cubic curves. And here are some graphs of polynomials of higher degree you may or may not have seen before. In this program, we'll become better acquainted with some of these curves. This one of degree 7 looks like a roller coaster. When a basketball player makes a beautiful shot like this, the ball's path is very nearly a parabola. Parabolas were studied by the Greek geometer Apollonius in the 3rd century BC. Much later, in the 17th century, Galileo showed that parabolas play an important role in physics. If you neglect air resistance, any projectile moves along a parabola if it is propelled forward and upward and allowed to fall under the influence of gravity. To make a sailboat glide smoothly through the water, naval architects use cubic curves to shape the hull. Sometimes pieces of several cubic curves are fitted together to form new curves called splines. This image of a television test signal is not the graph of a polynomial because it oscillates up and down forever. But part of it can be closely approximated by graphs of polynomials. Here are some approximations: linear, cubic, and higher degree. See how the polynomials fit the curve better and better as the degree increases. Two French scholars, Pierre Fermat and René Descartes, made a landmark contribution to mathematics in the 17th century when they introduced coordinate systems and described geometric figures with numbers and algebraic equations. For example, this line is described by the algebraic equation y equals x. If you take any point on the line, say this one, its vertical y coordinate is equal to its horizontal x-coordinate. If you move the line up by 1 unit, the new equation is y equals x plus 1. You can also move the line up by any amount, or down by any amount. This line is described by the equation y equals 1/2 x. For each unit you move forward along this line, your elevation increases 1/2 unit. Change in vertical distance divided by change in horizontal distance is called the slope of the line. parallel lines have the same slope. The equation y equals 2x describes a line with slope 2. The bigger the slope, the steeper the line. Horizontal lines have slope 0, and when the slope is negative, it's all downhill. The slope is the number multiplying x. Again, we can move a line up or down without changing the slope. Analytic geometry describes geometric figures by algebraic equations called Cartesian equations in honor of René Descartes. For example, a line of slope m has Cartesian equation y equals mx plus b. The Cartesian equation for this parabola is a storehouse of information about the curve. For any point on the curve, the vertical coordinate y is equal to the square of the horizontal coordinate x. The curve passes through the origin and is symmetric about the y-axis. The equation does not change when x is replaced by negative x. Let's see what happens to the equation when we shift the graph up or down. If we move the graph up 1 unit of distance, the new graph has the equation y equals x squared plus 1. If we move it vertically by any amount, the equation is changed by adding or subtracting that amount. All these examples illustrate vertical translation. Now let's see what happens if we translate the curve y equals x squared horizontally, say 1 unit to the right. To find the equation of the new curve, subtract 1 from x, then square the quantity x minus 1 to reach the original curve. Plotting this at x, we get y equals x minus 1 squared. This equation represents horizontal translation by 1. We can also translate the curve horizontally by any amount. You get the new equation by replacing x by x minus that amount. The graph is translated to the right of the origin if the amount is positive and to the left of the origin if the amount is negative. We can alter the shape of the parabola by a change of scale in the vertical direction. We multiply x squared by a scaling factor. The parabola opens upward if the scaling factor is positive and downward if the scaling factor is negative. Now let's start with the equation y equals x squared and perform all 3 transformations. Horizontal translation by an amount we'll call h. Vertical scaling by a factor we'll call a. And vertical translation by an amount we'll call k. No matter where we move the graph, y is a quadratic polynomial in x. To see this, square the quantity x minus h, multiply by a, add k, and rearrange the terms. The new equation expresses y as a quadratic polynomial in x. This number, which doesn't depend on x, is called the constant term. Changing its value translates the parabola up or down without changing its shape. The number that multiplies x is called the linear coefficient. Changing its value doesn't change the shape of the parabola, but it moves the curve to various positions in the plane. The shape of the parabola is determined by the number that multiplies the highest power of x, called the leading coefficient. If it's positive, the parabola opens upward like this, and there is a lowest point or valley on the graph. If the leading coefficient is negative, the parabola opens downward like this, and there is a highest point or peak on the graph. This point where the parabola has a peak or a valley is called the vertex of the parabola. The Cartesian equation can be expressed in terms of the coordinates of the vertex. Let's use Cartesian equations to find where this line intersects this parabola. Every point on the line satisfies y equals mx, and every point on the parabola satisfies y equals x squared. So, at a point of intersection, we have both y equals mx and y equals x squared. To find the possible values of x, we do a little algebra. And we find two intersection points, one with x equals m, and another at the origin. An arbitrary line may or may not intersect a parabola. If it does, the number of intersection points is either 1 or 2. Points where the horizontal x-axis crosses the graph of a quadratic polynomial are called real zeros of the polynomial. They can be found by solving a quadratic equation. The zeros are easy to find when the polynomial is expressed as a product of linear factors. For example, this product has one zero at x equals 2 and another at x equals minus 1. See what happens as the zeros move further apart or closer together. The lowest point on the parabola is always midway between the two zeros. When the two zeros coincide, the lowest point is on the axis, and we say the quadratic has a double zero. When a quadratic has no real zeros, like this example, it cannot be factored into real linear factors. Quadratic polynomials are used to generate these images of Jupiter. The computer must find the zeros of a different quadratic polynomial at each spot on the screen. If the quadratic has no zeros, the spot is away from the planet. If there is one double zero, we are at the edge of the planet, and if there are two zeros, the planet appears. Now let's look at some curves of degree 3, or cubic curves. 3 examples reveal the basic properties of all cubic curves. Y equals x cubed, y equals x cubed plus x, and y equals x cubed minus x. Each curve has two parts, one that bends down and one that bends up. The place where the upward and downward parts meet is called a point of inflection. The basic shapes don't change if we add a positive constant to move them up or a negative constant to move them down. In each of these two examples, the graph crosses the x-axis at exactly one point, even when the graph is moved up or down. But in this example, the graph crosses the x-axis at 3 distinct points. Adding a constant doesn't change the shape, but it can change the number of zeros from 3 to 2 to 1. These 3 examples, y equals x cubed plus x, y equals x cubed, and y equals x cubed minus x, can be regarded as the prototypes of all cubic curves. Let's see what happens as we change the coefficients in the equation of a cubic curve. Although the shape changes, it has the same basic form as one of the 3 prototypes. Or perhaps a mirror image. every cubic crosses the x-axis at least once. To see why, factor the cubic as the product of a linear factor and a quadratic factor. The linear factor has exactly one zero, which is also a zero of the cubic. In this example, the quadratic factor is never zero, so the cubic has only one zero. In this example, the quadratic itself has a double zero, so it can be factored and the cubic has a triple zero. Finally, in this example, the quadratic part has two distinct zeros, so it can be split into two linear factors. And we see that the cubic is a product of three linear factors and therefore has three zeros, one for each linear factor. This is what a cubic looks like if the three zeros are distinct, no matter how far apart they are. To understand why, let's follow the three factors from left to right. In this region, all three factors are negative, and the cubic takes negative values. Here, one factor is zero, so the cubic crosses the axis. Here we have one plus and two minuses, so the cubic is positive. Here the second factor is zero and the curve crosses the x-axis again. Here we have two pluses and one minus, so the cubic is negative. And here the third factor is zero and the cubic is zero. After that, each factor is positive and the graph continues to rise forever. Somewhere between the left two zeros, the curve has a turning point or a peak called a local maximum. And there is another turning point or a valley between the right two zeros called a local minimum. Now let's see what happens when these two zeros are made to coincide. Or when these two coincide. A more dramatic change takes place when all three zeros coincide. The peak and valley come together at a point of inflection. Computer-aided design uses pieces of polynomial curves to trace out shapes. For example, if you take two cubic curves and plot one against the other, you get a more flexible curve. Just the sort of curve you need to make a teapot. Here's a graph of a polynomial of degree 4 with 4 distinct real zeros. This polynomial can be factored as a product of 4 linear factors, and each factor corresponds to a zero. The shape of the graph is basically the same for all polynomials with 4 distinct real zeros. Between two consecutive zeros, there's a valley or a peak, or another valley. And here's what happens as two consecutive zeros are made to coincide. When 3 consecutive zeros coincide, a peak and a valley combine to form a point of inflection. Finally, if all 4 zeros coincide, we get a new valley whose floor is much flatter. Graphs of 4th-degree polynomials have 3 symmetric prototypes. Y equals x to the 4th, whose shape we'll call type 0. Y equals x to the 4th plus x squared, whose shape we'll call type 1. And y equals x to the 4th minus x squared, whose shape we'll call type -1. Together with an infinite family of asymmetric curves. Y equals x to the 4th plus x plus a number times x squared, where the number takes on all real values. The asymmetric curves we'll call type A. If you take any fourth-degree polynomial and change the constant term, the curve moves up or down without changing its shape. You can change from one type to another by adjusting the coefficient of x, or of x squared, or of x cubed. Every fourth-degree polynomial can be factored into two quadratic factors, and the polynomial has the same number of zeros as its factors. The number of distinct zeros can be none, 1, or 2, 3, or 4. For polynomials of degree 5, there are many more basic shapes. And for polynomials of higher degree, there are even more. In this program, we've become acquainted with polynomial graphs as they appear in a rectangular coordinate system. The graph of a linear polynomial is a straight line. The coefficient of x represents the slope, and the constant term tells us where the line crosses the y-axis. For quadratic polynomials, there is one basic parabolic shape. All others come from this by a combination of vertical and horizontal translation obtained by adjusting the constant and linear terms, or by a vertical change of scale. Parabolas show up as trajectories of moving bodies. For cubic polynomials, there are 3 prototypes. Every cubic curve can be changed to one of these 3 types by adjusting the coefficients. Cubic curves are used in designing many things. Everything from sailboats to teapots. Polynomials of degree 4 have these graphs as prototypes. As the degree increases, the number of prototypes also increases. We can change the shape of a polynomial graph with high-tech computer graphics, or with our own muscles. Here we see an athlete coordinate his actions to shoot a basket from the forecourt. What he's really doing is changing the coefficients of a quadratic polynomial by adjusting the position of his hands, and it all happens in a split second. Polynomial magic.